despite running a design software corporation for a long time and running a semiconductor business for over 20 years, I've actually been involved in test in a lot of ways over that period of time, right from the start, writing test programs and then having test as part of the business. And so in some recent talks I've given, I've looked at the history of all my perspectives of where test impacted business. And I thought it'd be good to look at, were there indicators we should have seen so we wouldn't have spent so long with brute force techniques? We could have anticipated when technology was going to change. So I'm going to take a look at some of those, looking back over my own history. Let's see if I got this. Yeah. So if we look at the semiconductor industry, for example, if you're in the chip business, when you try to develop and market new products, you look for differentiation. And that differentiation is usually either cost or price, performance, power, quality, being early to market, very important, and making your products easy to use in a variety of ways. And so you promote the product that way. But, I have never really seen someone try to promote a product as being tested more than the competitors. People look and say, what is your quality? That's a good metric, and you can even prove that. But they really don't care how much you tested it, except maybe military customers years ago, but still not much of a differentiator. And so it becomes overhead. The test engineer becomes like Rodney Dangerfield's. He gets no respect because you want to minimize him, not take advantage of him. And I found that is true in other areas. When I came into design software, I thought designer productivity ought to be a big differentiator. And so early on, I looked for design tools that made designers more productive. And the funny thing was, people would listen and they would say, yes, that's very good. We're glad to see productivity gains. But they would never buy because of productivity gains. They would buy because of other reasons, capabilities you had that they had to have. And I finally figured out that the managers, deep in their hearts, believed that those engineers really weren't doing anything on Saturdays and Sundays anyway, so why should I spend extra money to increase their productivity? So we had to focus on other issues. Well, in the test case, I go back to a period where I was running my first significant business, not far from here actually, at Texas Instruments. Let's see if I can get that. Oh, there we go. And this is late 70s, and we're building microprocessors, not very well, I might add. Motorola and Intel had sort of gotten the jump on us, and we had a 16-bit microprocessor family that didn't yield, wasn't reliably tested, actually wasn't in much demand either. But anyway, you run the business you're given. And so the first thing was to be able to get units that were in fact tested and would work. We thought that would be a good start. And so we started hiring product engineers. And I'll bet some of them are still in the audience today. Grady Giles and Dale Omard and Bob Conrad, Ron Norris ran this. All these people went on to do other things because we hired so many of them. I mean, we had at one point as many as 40% of our total engineering staff were product engineers because we needed to get these designs producible and functional. And the reason it took so many people was all the test was basically functional test patterns. And so we just kept writing more functional test patterns, and eventually things improved some, but clearly the quality of tests was a problem. And I didn't think of it at the time, I just worried, wow, we keep hiring more people, is this ever coming to an end? And yet the solution to the problem was right under our noses, and we didn't realize it. And that solution came from a custom design program that we had done about the same time with IBM. And IBM gave us a bunch of requirements, and we designed actually a digital signal processor for them. And it was an MOS design. Now, at IBM in those days, MOS was for memory and bipolar was for logic, so they didn't do logic chips with MOS, but they had this requirement they called level sensitive scan design, LSSD. And they handed us this spec and said, you have to do this too. And of course, we didn't know how to do it, so we had to sort of invent the way to put LSSD scan, in essence, structural scan, into the design. And it turned out they had built up this technology over many years. Eichelberger had a patent that goes back to 1972, and Tom Williams, 1979. And so they had not only that technology, but they had a hierarchy of technology that went to board and system level. And so we designed it and didn't think too much of it for a little while. But I remember this as a trigger for what happened next, because we should have seen this as an indicator of there was a way to simplify things, to automate tests, to break the test down into simplified pieces so you didn't have to understand the details of the circuitry to do the test, and so you could automate the test. And had we been thinking about this, we would have said, you know, there is going to be a big change. And so you think, oh, well, after you hired all those product engineers, you figured out there was a better way. Actually, the stimulus for adopting SCAN for us did not come from the efficiency of writing tests. It came for a totally different reason. And that reason was Kevin McDonough, who was the design manager for TI's original single-chip DSP at the time, was being badgered by the sales force because he didn't have an emulator chip. Now, in those days, when you designed a microprocessor, you had to design an emulator chip to go along with it that pinned out all the registers so that someone could develop an application and then debug the application using the emulator chip, and then they would plug in the real chip for the application. And you sold these emulator chips to HP and Tektronix, and they had development systems. Well, the problem with emulator chips was they were always one rev behind the actual design, and you didn't make very many of them, and they were a real pain, and the fab lost the recipe because you only ran one lot every 6 months or a year. And Kevin was trying to figure out how to get around that problem. And he remembered that thing called SCAN, or LSSD, and he thought, you know, gee, if I designed in SCAN, I would know the state every cycle in the machine, and I could just dump it out, and I wouldn't have to do an emulator chip. And so he actually reset the program, came back, designed in SCAN, and that's actually the only patent that TI has related to the single chip DSP, but it turned out to be a remarkable success at somewhat of a penalty. We actually increased the die size about 20% because we weren't very good at designing in SCAN, but we did it with full SCAN because we had to, the emulator had to work, and then found that when we got the chips back, instead of taking months to debug them, we could debug them very quickly because we had all this internal visibility. And so we then proceeded to design SCAN into all the DSPs after that, and later other chips. And it started to impact other parts of our business. One was in microcontrollers, and we had this requirement for the Delco microcontroller program for a ridiculous level of test grade, 99.49s. We couldn't possibly do it. Now, Delco, of course, had much smaller chips where it was possible, but we, at this time, were using actually IBM mainframes to do all of our simulation, test grading, and other things. And on an IBM 3090-600, the biggest of the mainframes at the time, we estimated it would take approximately 50 years to calculate the grade of the chip. So that was clearly not possible, and Delco became convinced that this thing called SCAN would in fact solve their needs as well for test coverage. And so it spread across the company. Ultimately, then, as JTAG came along in 1985, and this spread to the whole issue of scan at the board level, it now became the methodology. Still didn't stop writing functional tests, but it automated the whole process. It slowed the growth of the hiring of all those product engineers. And if we had done it sooner, the world would have been very different. So then, if I look at what happened next, I had the privilege of being very close to one of the next most revolutionary changes, and that change came with embedded compression. And maybe in retrospect it was obvious. At the time, we considered this was sort of speculative. The guys right down here in the front row was in pushing this as sort of a skunkworks program, but it was going to take money, and you were going to tell your customers they needed to design this stuff into the chip. And it sounded like a sort of a risky approach at the time. But in fact, if you had looked, or if we had looked at what was happening to tester costs, it would have been obvious that we were on an unsustainable track in terms of tester cost. And it's interesting that that same person who did the emulator chip and figured out that you could use scan for emulators, Kevin McDonough, became a member of our board. So when we weren't really sure about Adventure Graphics, what is this thing Janusz is talking about, we had Janusz present it to our board member, and he said, hey, you need to do this thing. And so Janusz went off and he did it. But if we had looked at the macro events in the economy, we would have seen some things. One was, at that time, integrated circuit design, chip costs per transistor coming down significantly, test cost not coming down significantly. If in 1999 you attended the ITC, you would have heard Pat Gelsinger, who was the chief technology officer at Intel at that time, say that it may cost more to test a transistor than it costs to manufacture the transistor. A pretty strong statement. Well, even more macro data. Now, being raised at TI, we believed in learning curves, and I can tell you that if you go and get the data from the SIA or from VLSI research, you can get the data for the revenue per transistor. You can't get cost per transistor, but you can get revenue per transistor, and you can also get the number of transistors produced each year. This is transistors absolute, counting how many transistors per chip, how many chips. And you plot it on a log-log plot with the cumulative number of transistors, and you find that the revenue per transistor in the semiconductor industry has been on a very predictable straight line forever. 1954 to the present, still on that line. Last year, the revenue per transistor dropped 30%. And it will this year as well. Very predictable kind of number. You can do the same thing, taking the data from SEMI for automatic test equipment shipments and how much is spent in the industry, divide by the number of transistors, and you also get a line that shows what that trend is. And notice the trends are converging. Test at that period of time, this is looking backward, at that time, we were seeing that this line was not parallel to this line, so test cost was becoming a bigger percentage of the total semiconductor cost. And once again, this is not sustainable. It can't go on. Something has to give. And the thing that solved that problem was embedded compression. So embedded deterministic tests announced here, 2001, and you would think, the solution is here. My pattern memories have been full forever. I can remember sitting through meetings when the engineers would present we've got a field failure problem, and I would say, well, just add some tests to weed it out. And they say, fine, just tell me which tests you want me to remove so that the pattern memory will have enough space for the new tests. And here, all of a sudden, an order of magnitude more room in the pattern memory. Surely this will be adopted very, very quickly and take off. Unfortunately, this product was introduced at possibly the worst time in history of any major innovative, certainly test product, but really almost any product, because the dot-com boom in the year 2000 led to a doubling of the annual purchases of test equipment, a record high, never since matched. People thought that the electronics world was going to the moon, so they bought enough test capacity to get us a few million miles down the road, and the next year, the bottom dropped out of the market. So if you have idle testers sitting all over your test floor, why would you be worried about compressing test vectors and reducing test time? Because you certainly are not going to give your customer a discount if you're an assembler, OSAT, or if you're a foundry of some sort. So no benefit and a new technology, so things didn't change quickly. But you'll notice that eventually test equipment costs picked up, and so we sort of worked through all that excess capacity, and you consider the reduced ATE equipment purchases after compression was introduced and its impact. Go back to that learning curve, and what you find is that with the new learning curve that resulted after compressed test was introduced, in the year 2012, there was $25 million worth of test equipment that was not bought, that in fact the industry didn't need. I ran into Alex Darbeloff in an elevator at MIT. He was the chairman of Teradyne and also chairman of MIT's Board of Trustees. And I knew him from past life when I used to buy a lot of testers. And Alex said, I just want you to know you have done more damage to the test equipment industry than any other person I've ever known. So I consider that a great honor. And in fact, if you look at the data, you find that now this is not transistors, this is devices, this is components. So we're looking at ATE capital cost, and you see the capital cost per component. Notice what happened after the introduction of of compressed test, and you can see as compressed test took off, so did the decline in the cost of test per device, and it changed the way we do tests today. So maybe there's some other indicators we should be looking for, and in fact, one I would suggest is, well, okay, when the embedded deterministic test was introduced, it was I guess I should say, intentionally constrained to 10x compression, thinking that, well, later on, maybe we can charge more for 20x and 50x and 100x, and I don't know, Janusz probably, at that time, in fact, we had set the goal for 1,000x. So there was really no need to constrain it to 10x, but in fact, people didn't need that much more. They had just gotten an order of magnitude until something happened in terms of the, oops, I skipped it. Let me go back. In terms of failures due to timing, the need for transition fault testing. And that, if we had been watching, came out at the 130 nanometer node, a paper presented, actually co-authored from NVIDIA, that was showing, in fact, where timing defects were causing a problem, and that failures due to timing defects had gone up a factor of 20x. And all of a sudden, word spread, and people started adding transition faults to their traditional stuck-at-fault models. And this required about 1.5 times the test pattern capacity. And as a result, all this benefit from compressing the test patterns now was being used up. And this continued. So as people added more fault models, as they added more tests, but particularly the transition faults added again and again. So we had this natural growth of Moore's law is pushing up the test cycles required naturally by adding more complexity to the circuits. But at the same time, transition faults on top of that, and this is a log scale, put pressure on the design for test software business to come up with new innovations. And as I mentioned, a goal was said, we ought to get up to 1,000x compression. That's 3 orders of magnitude increase in capacity. And so step by step, various types of enhanced compression, efficient X handling and broadcast, multi-channel, and ultimately test points insertion added that capacity. So today, if you actually go back and measure where are we today versus year 2000, it's about 1,000x improvement, all sort of predictable. If you build it, they will come. You give them the capacity, they will find the fault models to use it. So what else? Well, diagnosis-driven yield analysis was sort of evolving all this time. And initially, one of the principal needs was the fact that the failure analysis labs had gone from being a relatively inexpensive operation to being fairly difficult. So you no longer could use just a regular microscope. Of course, we had scanning electron microscopes. We had devices operating in electronic equipment, but it was quite difficult to find defects, and especially systematic defects that were a part of the process or the design. And the equipment was becoming increasingly complex. And so failure analysis labs were expensive things. They took time. They had trouble finding where the defect was, what the problem was. And meanwhile, the geometries continued to shrink. And as a result of that, it became more and more difficult to find where a defect was, what the defect was, and what I could do about it. And yet, once again, right under our noses, we had the ultimate in virtual test. We had, in fact, by using scan diagnosis, you could find certainly logic faults quite easily. And so instead of dozens or hundreds of test observation points, you could look at millions of observation points and you could identify a problem pretty easily. And so if you go back and trace the literature, you can see where people started taking advantage of this because time to market was really a key parameter in the semiconductor industry. And yes, oh, there we go. And so if you can ramp up a new process, a new product, faster than your competition, a large share of the profit lies in the early phase of the use of that product. And looking at papers, for example, that talk about moving the ramp curve to the left and ramping faster. There's one from ST that appeared. If you look at just the issue of yield excursions, where you've got a stable yield, but all of a sudden it goes out of whack. We have examples. Well, I'm out of sync with slides. Anyway, one from Cypress Semiconductor, ITC poster board. And then we have, in the case of mature yields, the fact that soon, there we go, Freescale publishing a paper related to the improvement of mature yields through diagnosis-driven yield analysis. But most of these early reports were finding defects, even systematic defects, but defects, and then working down to the root cause without having to do failure analysis in the laboratory. But overall, the big move was from diagnosis to just a broad yield improvement. And that meant that you had to do a lot of deep data analytics. You had to, of course, identify defect types and systematic fabrication problems. But in addition, you had to take that data and separate it from the noise, look at millions of devices, and do root cause analysis. Now, one of the things I think when I go to keynotes, if the presentation is a combination of all the things I already know put together in a different way, it may be nice, but you really ought to get some original data. So I challenged our people, said, what can I point out that is not generally available information? And of course, one of the things that's not generally available is what everybody is actually using. But we have that data because we sell them the test software. We know how much they use. We know which programs they use. So without identifying individual customers, I can tell you how broadly are these things actually used. So what I've done here is to look at diagnosis-driven yield analysis technology and what's happening to the adoption. So if you look just at scan diagnosis, basic logic problems, and you look at that curve, 2015, you notice here we are talking top 10 semiconductor companies. Now, how do I know the top 10 semiconductor companies? Well, the top 10 semiconductors companies buy a lot of test software, so I know which things they're buying. And I also know how much they're using because they come back and try to buy more software when they're fully utilizing what they have. And what you can see there is for scan diagnostics, they're up above the 80% point. Now, if you throw in the layout influenced yield analysis and take one more level of sophistication, then layout aware diagnosis-driven yield analysis is almost at the same point as regular scan diagnosis, and the overall yield analysis, the whole enchilada of looking at the systematic yield problems and the deep data analysis of those systematic yield problems, we're up around the 70% point today, and in all cases we're heading to the 100% point, where people will analyze every failure that occurs, build that into a database, take that information, and identify second, third, and fourth order effects. Now, the other thing is that one big source of data is the foundry that runs your wafers. And in fact, historically, foundries, for legitimate reasons, have in fact kept that data quite confidential. So it's your design, you're buying the wafers from the foundry, but the fact is traditionally they didn't share that data because after all it was proprietary. They didn't want you to switch foundries, so after all, if you knew all that, that would be easier to switch, and they didn't want you to know actually what the internal data was in terms of trying to track their process and so on. And that became a barrier, so the fabless company on one side had its own yield diagnostics, the foundry had its own, and what's happened is, of necessity, that data is being shared. So if you look at certainly the big company contracts with the foundries, they require sharing of that diagnosis data, and if your company is not getting that benefit, you need a better negotiator for your next contract. Excuse me. What about the actual diagnosis? This is another number that I'm sharing with you that I don't think is generally known, is just how many die are actually diagnosed using this kind of software. And so all we did was just take the top users and just count up how many devices do they actually diagnose. Well, I was somewhat surprised. Per day, today, over 600,000. This is a minimum because we know they have bought enough software and used to capacity, and they are now doing 600,000 per day. and they are on their way to 1 million a day. And I think this greatly understates the problem, because I know at least 2 major companies that analyze every device failure and throw it into their database. Now, are there publicly available indicators of yield improvement awareness? And I had to look pretty hard for that, but I found that too was right under my nose, because at least a couple times a year I go to Taiwan and I visit Taiwan Semiconductor. And years ago I used to go in there in the lobby, and we'll see, we would see their symbol, and just as I was waiting in the lobby, I would count the number of defective die on their wafer. And I noticed that there were, oh, thank you. Well, I already had one, but there were more than 20 defective die. And guess what happened in 2005? This is registered with the Patent and Trademark Office in 1994, 20 plus defective. And in 2005, we found that the symbol became more readable and the number of defective die decreased by 50%. So I offer that as evidence of the awareness. I actually checked with the management, and they told me, yes, we did change the logo. We'd rather you didn't point that out, but it's okay. They can handle it. Okay, well, so let's move on to one of the next things that changed the world, at least that was in my sphere of observation. And this one, I really had trouble figuring out what the early indicators were, because Friedrich Hapke had been working on this for a long time, and I guess we should have guessed, but the indicators came in 2 places. One is really big die, where we had such complexity that we needed new fault models to test. Stuck at and transition, even bridging faults, was simply not enough. But the thing I didn't anticipate was that in older designs, smaller designs, that the pressure from companies like automotive companies to get down to 1 DPM or lower would cause people to start thinking for additional ways to improve the coverage of their tests for all kinds of faults. And at the upper end, there certainly was a trend occurring. The defects within blocks now became material. So the blocks in a standard cell design got bigger and bigger, and there were more ways to embed failures. And so, of course, we could develop test vectors by looking at the IOs of those cells, but as you got below 90 nanometers, there were potentially other kinds of faults that could occur for which you would not be generating test patterns. And the thing that I found so novel about the cell-aware methodology was you turned the whole methodology upside down. As in the past with ATPG, you target faults with a specific set of fault models, and you write the test vectors to cover those faults. But with cell-aware, you start from the other end. You start with the defects themselves, and you look at all the ways that it could fail at the transistor level, all sorts of types of defects that could occur, and then you simulate those, and you figure out what test patterns could I write that would be at the gate level, at the I/O level, but that would provide that coverage. And actually, Friedrich, the winner of the Madge Award last year, did in fact come up with a whole methodology, and the surprise was that a number of papers were published where people showed that as many as 1,000 DPM, or in the AMD case, 800 DPM turned up, and since then a lot of others have turned up this kind of magnitude of failures that were never tested for, and that in fact greatly changed the level of quality that we could provide to customers, and in fact, even in less complex parts, potentially an order of magnitude improvement in the coverage as a result of it. The problem, the use of cell-aware technology expanded the number of tests required. So our pattern memories, although we were already compressing at 500, 800x the original level, there simply wasn't test capacity for this because even though it's a superset of all the other tests, it's about 1.7x the existing amount of test pattern memory required. And so the fortuitous thing was right about the same time, or a little bit later, the world moved to a higher level of test compression through another set of innovations in test points, and that added pretty consistently 2 to 4x the capacity of memory, the capacity for test. And so a lot of people were able to move quickly in adopting the more advanced cell aware. And the other side was that it worked in reverse, as actually was presented by Bill Maxwell a year ago. You could, I think, let's see, okay. Well, let me tell you, you could start with the test failure and work your way back to the cause, because now you had a model for all sorts of different faults. And if we can ever, oh, there's the slide, actually stolen. The cell-aware diagnosis now gave you the resolution within the cell to identify the exact cause of the failure, something that people had never imagined you could do before with that level of resolution. And so once again, I present some data that has not been publicly available that says how many people actually use this stuff. And there you see the 2015, and you see the vector of adoption saying, about 20% of the top 10 semiconductor companies are actively using cell-aware technology, and based upon the rate of adoption, that's going to be 60% by the year 2020. Pretty rapid adoption of new technology. What else? How about hierarchical test? So this one I view as somewhat evolutionary, but it's driven by a lot of factors, mainly designs getting too big and the individual blocks getting too big, but it's also driven by the efficiency of developing test programs. So what I mean by that, I think it's fairly obvious that as you get bigger and bigger blocks and you see more and more instances across a chip, then you need to divide and conquer. Those duplicate blocks can use the same patterns. You put a wrapper around them and then share scan channels and in effect dramatically improve utilization by not having to have independent test vectors for each of them. But the other impact it has is a shift left. It means that you can start and get the tests generated as you complete the individual blocks. That brings tests forward. That leads to less pressure on the test engineer who's trying to get the test patterns run toward the end of the design when everything else is hectic and you're trying to get it all together to get a tape out. Now, this way, you have it done much sooner in the cycle and have a much better chance getting everything done quickly and efficiently and with far fewer tests generated for testing the actual device. And if you look at industry results, the benefit, in addition to moving things earlier in the cycle, I can look at who actually uses hierarchical test, and the answer is roughly 50% of our top 10 customers are actively using it, and another 20% are adopting it now. And just looking at runtime reduction, an average of about 10x, memory footprint about 5 to 10x, and pattern count something in the 1 to 2x range. So a pretty big benefit, and one that I think adoption will increase with. So now we come down to the present time, and we look for current indicators of what's coming. And there's some, once again, this is a difficult task because these things are just emerging, but what about, wow, it's fast. What about in-system test? Well, this has been around a long time. We've had built-in self-tests for many years, and in fact, people who do systems like Automotive that have to do a startup self-test have been implementing that. People who design the chips have been doing that. But the thing that has really caused it to take off is the product recalls and the implementation of ISO 26262, which now our customers in the automotive industry have become very sensitive to. They've become sensitive for a reason, and so have their semiconductor suppliers. The semiconductor industry is supplying chips to automotive semiconductors that, in fact, since I have no way of figuring out which slide we're looking. Oh, there we go. So it's about 10%. About 6% of all semiconductors shipped. Second largest segment of the semiconductor industry, and in fact, the automotive industry has a big problem with warranty costs. Amazingly, they've been holding those costs relatively flat. I think when you see the Volkswagen results in 2016, that may rise, but it really amazing, it's only $10 billion. But now automotive customers are now under a constraint in design that comes along 26262 that says that you have confidence in the use of the software, you're using best practices, and in fact, it has a bit of a vague description of components will in fact test themselves. Well, you've seen simultaneously lots of semiconductor manufacturers advertising the built-in self-test capability in their chips. This one's Freescale. There are many more that in fact have been advertising this capability. Automotive manufacturers have been designing it in, and this is really good. Okay, yes, it'll go. I know it'll go eventually. No, yeah, there we go. Renaissance
Here, power on self-test. So very basic. You start up your car, it does power on self-test. So you build in self-test, been around a while, pretty straightforward. But in fact, because you had compression to manufacture the parts, why not combine the built-in self-test with the compression? That's becoming more common. And then the next one is, you really need to have these components testing themselves during time slices when they're not required to be doing other things in terms of operating the car. And so why not insert test points so that you can use that slack time in the test? And so how many people are actually doing this? Well, once again, we can look at our customer list, see who's building integrated circuits for the automotive industry, and you get the result that the percent of customers, since there's nothing there, I'll have to percent, we lost it. Let's see, try again. Percent, oh, wow, we're back again. Percent of customers that are making automotive ICs with digital content that are using various BIST technologies. So if you look at the left, that's just plain old BIST. You look BIST with compression, then in the third one is with power on self-test, and the last online BIST is with test point insertion in order to have dynamic
testing. And you can see of the automotive customers, over half are already at the last stage, and everybody's on a vector to move up to near 100%. Okay, let's take, one more for the present. Let's look at analog mixed signal test automation. And here, there are a number of factors driving that. But I think the biggest one is the fact that every year we say the biggest opportunity for progress is analog, but analog tests moves at a snail's pace. And yet, if you look at a paper from 2 years ago at ITC from George Gielan, he was noting that, that analog ICs in fact make up the majority of what goes into the automotive semiconductors, let's see. Oh, there we go. That's the blue part, all the analog integrated circuits. And he showed a chart along with that. And that was the parts per million that were detected, typical for an automotive chip. And you notice it was improving, parts per million defective was improving, declining on a linear scale quite regularly until recent years. And there you see it went flat. That I consider to be a leading indicator. That is a non-sustainable situation. That means ultimately we will improve analog test. How will we improve it? Well, it will be probably a series of innovations, but certainly one of the things to improve the quality and reliability of analog devices is to be able to measure the quality of tests, effectively test grade, and be able to detect and weed out the outliers so that you may very well have a group of devices that on a particular test all test similarly, they all pass, and even this one down here passes. But is that statistically significant? Should you be worried about a parameter excursion that is not in line with the others? And the answer is that needs to be done statistically, quantifiably. You need to build a database and a set of models, and that, I believe, will at least be one of the steps that occurs, certainly in the near future, to improve the quality of analog tests. And lastly, just looking to the future a little, I have to say that the the one thing that I know has to emerge is the ability to do real-time in-system tests for safety requirements. So monitoring aging, degradation, and being able to predict the about-to-fail devices is something that we will be pressured by, particularly the transportation industry, cars, planes, and trains, to in fact do. And I would note that this is a technology that requires deep data analytics. This is a technology that is in broad use today in many different ways. And I point to the example of aircraft manufacturers and their suppliers. So the amount of data generated by an airplane is about 10 terabytes every 30 minutes. Everything about that plane is being recorded, and in fact, the manufacturers of those engines have access to all that data, they collect all that data, and they analyze all that data in depth. And with that, they are able to predict when maintenance is required, when there is an imminent failure, or even when there is just gradual aging that needs to result in some kind of action. And it turns out that that data is more valuable than the engine itself. And so ultimately the speculation is that they ought to just give away the engines and sell a maintenance contract because that data is proprietary, they have it, they understand it, and they can charge a monthly fee that will in fact create a stable stream of revenue as long as those planes are flying. And the data exhaust, as it's described in an automobile, is quite similar. Maybe not the same consequences if there's a failure, but still that data is being collected, will be collected more and more. A lot of activity in new cars, in the connectivity, and ultimately the value of test data will increase. So as I started out, the test as an overhead has really become test as a value creator. And more, the yield improvement, the reductions in test cost, and the improvements in test quality have become measurable parameters for why your test engineering group is not overhead, it's valuable. And in the future, it could in fact be the store of value that creates what you sell customers, what you provide, and the value you create. Test engineering and design for test are a remarkable field with a remarkable number of innovators, and I personally am proud to have been around it throughout my career and witnessed it happening. It's been great.